Hello, welcome to Module 4, Part 2. And so we're going to talk briefly about the first law of thermodynamics, talk a little bit about temperature, phase change, and then the second and third laws of thermodynamics. So we had talked briefly about how the first law states that energy in a system equates to a change. And so work done on the system is equal to heat done at the system, meaning that heat or thermal activity is the same thing as general energy or work. And one of the best ways to perpetuate this knowledge is the Joule's experiment. And so here is James Joule, the father of the first law of thermodynamics. He also came up with the caloric system and talked about all sorts of hypotheses that have to do with calories, meaning specific heat, the concept of specific heat. And his experiment was pretty simple. Basically, there is a weight that has an equal amount of poundage as the amount of poundage fueling the heat that's coming out of the Bunsen burner, and we can heat the water and we can turn the turbine, and we will find that the same amount of work done on the system with the same amount of water, so same mass of water done here as the mass of water done here, will make the temperature raise the same amount. And this proves that first law, that they are the same thing, that work done on a system, energy added to the system, regardless of how I add energy to the system, can change the active state of molecules, make them vibrate faster, which in return means that when I measure their temperature, they will measure at a warmer temperature. Once again, temperature is a property based on contact sensation, so it's a measurement. It's something that I sense or feel. One of the best ways to measure the amount of heat energy within a system is a simple equation that you may have learned in chemistry. This is actually a very common chemistry-based equation, and it basically is the Q, once again meaning thermal energy, is equal to the mass times the specific heat times change in temperature. Or if I want to find how much the temperature will change, I can take the heat energy in the system and divide it by the mass divided by the specific heat, right? Specific heat is a standard number. It's the amount of energy needed to raise something's temperature. And that's something that's set. If you're a metal, you require a certain amount of energy to raise your temperature up 1 degree. If you are a piece of carbon, you're going to require a certain amount of energy that will be different than a piece of copper, for example. So that is something that I can actually look up on a table. And this is my lovely specific heat table. Do not ever, ever, ever alter your specific heat. That is something that whatever the standard equation is that it comes with, it's something that you look up on a table because it's something that's measured standard in a laboratory. It's true universally. This substance will change its temperature 1 degree if this much energy is added to the system. And so specific heat in the system international units is here. So it's joules, kilograms over degrees Celsius. And specific heat in the US system is BTUs, pounds, degrees Fahrenheit. So if I'm working with a number where I want to find change in temperature in degrees Fahrenheit, I will use this part of the table. If I'm working with numbers where I want to find temperatures in Celsius, for example, I will use this part of the table, right? Or if I want to know how many joules, how much heat energy I'm getting out of the system, I will use this part of the table. If I want to know how many BTUs I'm getting out of the system, I will use this type of the table. So use the proper part of the table depending on what type of answers you want in your questions. Which brings us to that contact sensation. If temperature is based on contact sensations, that means that different things will act differently at standard states of temperature. And this is where we get into Newtonian phases. So Newtonian phase change is your standard solid, liquid, gas, the thing that you learned in elementary school, where solids will act solid and they will not take on the shape of the container. Liquids will fill the shape of container, right? And gases will fill the shape of container and stream out of the container and then some. They will fill any space to their fullest, because they have that amount of space to fill. So they will keep moving farther and faster and apart, and so on and so forth. There is the non-Newtonian phases, and that's where we get into the Boltzmann complex and plasmas and things like that. Those are non-Newtonian phases. And so down in this little system, I've got plasma up here, a bunch above gas, which is different than gas. It acts differently than gas. But that wasn't your standard original system, right? And plasma is something that's kind of hard to find. Our sun does plasma, right? That's the phase change that's taking place on the sun with gases. And lightning, when lightning strikes, plasma does shoot off from the top of a lightning strike. So lightning produces plasma. So we do see plasma production on planet Earth, but it's not common the way that solid liquids and gases are, right? Our Newtonian phases are. So there's three transfers, or three ways heat can transfer in a principle of an object. And this is where we get into conduction, convection, and radiation. Conduction is the standard heat transfer of molecules colliding with one another. So I can conduct heat through one object to another. You think of the spoon left in the pot, right? I leave the spoon in the pot on the stove boiling. The heat of the stove heats up the pot. The pot is touching the spoon, therefore it excites those molecules get excited, it runs up the spoon, then I touch the spoon and I burn my hand because the heat moved from the spoon to my hand, burning it, right? So that's conduction. It's all contact heat. And we can express this as a standard set of equations as well. So transference or collision of conduction is based on heat transfer viva conduction based on time elapsed. So QC, once again, thermal. So this is thermal heat, and little c in this abbreviation, they always go together, Q and C in this concept, and it means heat transfer, thermal transfer within an object. And little t, once again, is over time. Or another way to express it is thermal conductivity of the item times the area of the item times its change in temperature divided by its thickness. Because a really thick item will take longer to heat up than an item that is thinner, right? The transference will not take as long. If I have something that is paper thin, the temperature transferring from one side of the paper thin object to the other side of the paper thin object will take a lot less time than the amount of time it would take for something that is 4 inches thick. So, the spoon example, there you go, and transference of heat energy. Some of the equations that we'll play with this will be in the energy analysis, and we'll talk more about home heating analysis and things like transference of heat energy through window surfaces and walling surfaces and adding these things together. And that's where conduction is going to come back literally in the next module. So we'll come back, you'll see it again, but I'm going to introduce it to you here so that we're starting to wrap our head around it. Quickly before I jump on, convection, because we did conduction, I'm pushing now in, but convection is the set of within its own substance. So you think of a liquid, and the warm molecules within the liquid are moving farther and faster apart, therefore they have less density and they rise to the top, and the cooler ones are displaced, and so they sink to the bottom, and you get this rotation. You can get a convection cell, right? But that's within itself. So convection takes place within itself with the heating and cooling. And convection we're going to talk about again when we talk about solar hot water heaters and how those work, because they're really working based on convection. And then radiation is the act of radiant energy leaving your body when you're producing heat, because you can't seem to keep it all in one system. And so you can think of you sit in a chair. You leave that chair, somebody else comes in the classroom, they slide into that chair, and it's warm, and you're like, ew, there's a warm chair under my butt. What happened? You guys were in conduction, right? But sometimes you can take and you can hover your hand over that surface, and you can feel that heat radiating off that surface. That's radiation. That's actually heat energy leaving that system set. And so you can feel it at a distance leaving a substance, especially if there's a difference in equilibrium, which is why I'm coming back to this second law. So based on the direction of physical processes, things go in one direction, not the other, and that is a system with less energy will move to a system that is, sorry, I'm saying it backwards. A system with more energy will move to a system with less energy. So the hot source will move towards the cold sink. And on that note, I'll pick up with part 3 and my last part for module 4.